oyster shells into Charlotte Harbor today to help boost water quality and help our fish and anglers. The shells act as a natural filter to get toxins out of the ecosystem.
For almost 20 years, trucks rolled quietly toward the Florida coast, carrying something most people would call garbage. Not glamorous cargo, not scientific equipment, not anything anyone would fight over. Just shells. Oyster shells scraped off restaurant plates, swept out of seafood processing plants, and piled into dumpsters behind kitchens from Tampa to Pensacola. Between 2007 and 2024, hundreds of thousands of tons of this so-called waste were collected, cured, loaded onto barges, and lowered into the waters of Florida's Gulf Coast, much of it concentrated around the Big Bend region near Cedar Key. On paper, it sounded like the kind of idea that gets laughed out of a budget meeting. In practice, it became one of the most quietly remarkable ecological turnarounds documented on the American coastline in the last quarter century. To understand why anyone thought dumping shells into the ocean was a good idea in the first place, you have to understand what Florida's oyster reefs used to be and what they had become. Oyster reefs are not just piles of shellfish. They are three-dimensional living structures, built layer upon layer over centuries, as one generation of oyster settles and grows on the shells of the generation before it. A healthy reef can be centuries old, dense enough to break waves, complex enough to shelter hundreds of species, and productive enough to filter enormous volumes of water every single day. Florida's Big Bend coastline was once home to reef systems like this, stretching for miles along the Gulf. But decades of overharvesting, altered freshwater flow from upstream rivers, pollution, and coastal development had done what they usually do to slow-growing marine habitat. They gutted it. By the early 2000s, researchers at the University of Florida documented reef loss along parts of the Big Bend approaching 90%. Oyster larvae, drifting through the water in search of hard surface to latch onto, were finding almost nothing. No substrate, no settlement, no next generation. A self-sustaining system had become a dead end. That is the problem a small group of researchers and state agencies set out to solve. And the tool they reached for was almost embarrassingly low-tech. Oysters need calcium carbonate to build on, and it turns out old oyster shells are close to perfect for the job, both physically and chemically. Rather than manufacture artificial reef material from concrete or limestone, restoration teams working through Florida's Fish and Wildlife Conservation Commission, the University of Florida's Shellfish Extension Program, and a rotating cast of local partners decided to close the loop. Shells that would otherwise be trucked to landfills were instead cured, cleaned, and returned to the water as the base layer for new reef. The flagship effort became known as the Lone Cabbage Reef Restoration Project in Sewanee Sound, led in large part by researchers including Bill Pine, Peter Frederick, and Leslie Sturmer, with support from the National Fish and Wildlife Foundation's Gulf Environmental Benefit Fund following the Deepwater Horizon settlement. Smaller parallel programs sprang up along the Panhandle and around Tampa Bay, recycling shell from local restaurants bucket by bucket. The public reaction was not universal applause. Environmental advocates raised real concerns about dumping any material into sensitive coastal waters, worried that shell piles could smother fragile bottom habitat rather than help it. Commercial fishermen and charter captains, many of whom had worked those waters for generations, were openly skeptical, having watched other well-intentioned restoration projects fail to deliver much beyond a line item in a government report. It was not an unreasonable position. Traditional artificial reefs, built from sunken ships, concrete rubble, or so-called reef balls, have a well-documented weakness. They tend to attract fish that already live nearby, rather than create new ones. A structure can look impressive on a fish finder screen, while doing almost nothing to grow the actual population of the ecosystem around it. If oyster shell reefs were going to be more of the same, critics argued, they weren't worth the barge fuel it took to dump them. What happened instead took the restoration teams themselves by surprise, and it started at a scale too small to see with the naked eye. Within days of shells settling onto the seafloor, bacteria began colonizing their surfaces, forming biofilms across the calcium carbonate. Those films were not incidental. They were the opening move in an ecological chain reaction. Oyster shell is made largely of aragonite, a form of calcium carbonate that dissolves gradually in seawater. gently raising the local alkalinity around each shell fragment. That small chemical shift happens to be exactly what young calcifying organisms, barnacles, tube worms, and above all juvenile oysters, need to attach and begin building their own shells. In effect, the discarded shells were not just offering physical surface to grow on. They were subtly changing the chemistry of the water around them in ways that favored the next generation of reef builders. Within weeks, diatoms and microalgae moved into those biofilms. Small grazing invertebrates followed to feed on them, and the first juvenile fish began showing up to feed on the grazers. A functioning food web, invisible from the surface, was assembling itself out of what had been thrown away seafood scraps. This is the part of the story that sandy, featureless seafloor simply cannot replicate. Soft bottom offers nothing to hold onto. No chemical microzones, no structural crevices, no stable surface for a barnacle or an oyster larva to grip. It is, ecologically speaking, mostly dead space. The shell deposits bypassed that limitation entirely, giving marine life a foothold where none had existed. Within the first year of many deposits, researchers documented juvenile oysters settling onto the shell in far greater numbers than the sandy control sites nearby, which supported next to nothing. By the second year, those juveniles had matured into reproducing adults, spawning a new generation that settled directly onto the structure their parents had built. The reef was no longer something people had made. It was something oysters were now making themselves, generation stacking on generation, vertical growth adding height, while horizontal spread pushed the footprint outward beyond where the shells had originally been dropped.
Fish did not take long to notice. Reef structure of any kind changes the physics of a stretch of open water, breaking up current, creating shadow and shelter, and offering ambush points for predators and hiding places for prey. Redfish moved into the new reefs to feed and take cover. Sheepshead arrived to graze on the invertebrate communities coating the shell surfaces. Flounder worked the sandy edges where reef met open bottom, and species like snook and mangrove snapper began showing up in numbers that hadn't been recorded in those waters in years. Local charter captains, several of whom had testified against the shell program when it was first proposed, began quietly changing their minds as they watched fish stack up around structure that hadn't existed a few seasons earlier. Some went further, formally asking the same state agencies they had once opposed to place new reef material near their favorite fishing grounds. It's a rare thing to watch a stakeholder group flip from opponent to advocate, and it happened here largely because the fish showed up and stayed. The ecological story didn't stop at fish, either. Oysters are filter feeders, and a single adult oyster can process tens of gallons of seawater a day, straining out suspended sediment, excess nutrients, and bacteria as it feeds. Multiply that by the hundreds of thousands of oysters now colonizing restored reef, and you get something close to a natural water treatment system operating around the clock with no electricity, no maintenance crew, and no budget line. That matters enormously along Florida's Gulf Coast, where nutrient runoff from agriculture and coastal development has spent decades fueling harmful algal blooms and red tide events that periodically choke off oxygen and trigger mass fish kills. Reefs dense with filter-feeding oysters attack that problem directly, pulling excess nutrients out of the water column before they can feed a bloom. Clearer water, in turn, allows more sunlight to reach the seafloor, which supports the return of seagrass beds, critical nursery habitat for juvenile fish, manatees, and sea turtles, in areas that had been too murky to support them. Seagrass then helps stabilize sediment and further improve water clarity, creating a second feedback loop layered on top of the first, each one reinforcing the other without anyone directing it from above. Then came the storms, which is where a project like this either proves itself or gets quietly abandoned. Hurricane Irma struck the Gulf Coast in September 2017 as a major hurricane, bringing the kind of storm surge and wave energy that reliably strips beaches and reshapes shorelines overnight. When damage assessment teams surveyed the coast afterward, stretches of shoreline backed by restored oyster reef had held up noticeably better than unprotected sandy shoreline nearby. The mechanism is straightforward once you think about it. A dense, irregular, three-dimensional reef structure absorbs and breaks up wave energy before it reaches the shore. the same way a rocky shoreline dissipates surf better than a smooth beach does. Concrete seawalls and rock revetments can do something similar, but they are expensive to install, require ongoing maintenance, and eventually crack, shift, or fail outright under repeated storm loading. Oyster Reef does the opposite. Storm damage that knocks loose shell material simply creates fresh surface for new larvae to settle on, meaning each storm the reef survives tends to leave it larger and more complex than before, not weaker. It's a coastal defense system that repairs itself at a fraction of the cost of traditional hard armoring and gets stronger with age instead of wearing down. By the early 2020s, the story had moved well past the reefs are surviving into the reefs are still expanding. Some of the oldest deposit sites had grown well beyond their original footprint, with new structure radiating outward from the initial shell mounds as successive generations of oysters settled, matured, died, and left their own shells behind as substrate for the next wave. What began as loose, irregular piles of dead calcium carbonate had, over roughly 15 years, developed into architecturally complex reef with vertical relief, overhangs, and interlocking surfaces, the kind of structural variety that supports dozens of distinct microhabitats within a few square meters. Crabs, octopus, sea stars, and juvenile fish were all exploiting different pockets of that structure at once. Researchers studying carbon cycling in restored oyster reefs have also started pointing to another benefit that wasn't part of the original pitch. Oyster shell and the sediment that accumulates around healthy reefs can lock away organic carbon that would otherwise cycle back into the water and atmosphere, adding a modest but real climate angle to a program that was originally sold purely as habitat restoration and water quality work. None of this makes the Florida Shell program a perfect or unlimited solution. It works because it solves a very specific bottleneck, a coastline that had plenty of oyster larvae drifting through the water, but nowhere for them to land. Give those larvae a stable, chemically favorable surface, and biology does the rest, largely for free and largely without a maintenance contract. That is a different proposition than restoring a coral reef damaged by warming water, or rebuilding a wetland that has been converted to farmland, where the underlying stressor is harder to remove. But within its own lane, the results have been persuasive enough that similar shell recycling and reef restoration programs have since launched in Alabama, Mississippi, Louisiana, Texas, and as far away as New York Harbor, where the Billion Oyster Project has applied much the same logic in one of the most heavily altered urban waterways in North America. Coastal engineers in several other countries have started studying the Florida model as an alternative to pouring more concrete along eroding shorelines, drawn by a simple pitch. Let organisms that have been building coastal structure for millions of years do the job they already know how to do. What makes the whole story worth telling is not just that it worked, but how quietly it worked. There was no single dramatic breakthrough, no press conference moment where scientists declared victory. It was bacteria colonizing shell surfaces within days.